Hello everybody and welcome to this presentation on Java Performance Update version 25. And it's very rare that we have the Java JDK number 25 that aligns with the number of the year. It will take a very long time before next time we will see that happen. I think it's beginning to look like a tradition to come here and talk about Java performance. But this year it's going to be even more action-packed because we have not one JDK release, not two, but four, because we have this LTS version 25. And I think many of you are considering going from 21 or some earlier version to 25. My name is Minborg. I work in the core library team at Oracle. And starting off, we can take a look at some overall figures. There is a standardized way of measuring performance called SpecJob 2015. And of course, this is just one benchmark, but that benchmark is trying to include a lot of workloads and gives you a kind of indication on what kind of progress that has been made. So looking at the first one on the left-hand side, the bar there says critical JOPS. That is kind of a measurement of latency. So we will see latency dropping about 10% by just deploying the latest JDK. You don't even have to recompile your code. You just deploy it with the new JDK, and you get a much more consistent performance. Looking at the right-hand side, there is something called max JOPS, which corresponds more to the throughput of your application. And there we will see about 5% increase, again, just by switching to the new runtime. And you should remember that it's pretty hard to even, get a fraction of a percent to get bigger because the JDK is already so optimized. So we are very happy in the JDK community to see this figure here. And looking back even further, if you have an older version, who here is stuck on 8 in some kind of version? It's quite few. But if you are, you will see a tremendous performance increase if you have the effort and time to actually migrate. So we will see more than 100% better in terms of latency. And you might wonder, well, that means that we have negative delay, but that's not the case because the figures here are defined as the difference divided by what's been there from the beginning. And it's almost a third that you can shave off in terms of performance. And all these translates to costs because if you run in the cloud, you usually pay for the resources you have. And now if you go from 8 to 25, you can suddenly have 1/3 less resource, pay 1/3 less. And here is another example. This is one of those microservice frameworks, and there we saw a significant gain. Okay, so here is the agenda. We're going to talk about some performance metrics, some challenges when you measure performance. We're going to talk about some tricks that the JIT compiler or the C2 compiler can do for us in order to understand the things we have changed. Then there is 13 performance improvements. And there is a story behind this figure 13. I told my wife that this spring I'm going to Antwerpen this autumn. And I'm going to talk about 8 performance improvements. And she said no. And I said, well, what's wrong with Antwerpen? Have you seen the Central Station? It's very nice. And she said, yeah, there's nothing wrong with Antwerpen, but don't use the figure 8. 7 is better. And I said, well, I mean, every number is born equal, I said. And at that moment, I know I lost my argument because I picked 8 because we program like 8 because it's a power of 2. And then I didn't give up, so I said like, maybe I have some more improvements. What about 16? Because that's even better. It's 2 to 2 to 2. And she said like, no, you should have 13 or 17. 2 new primes. I was shocked. But okay, you know how it is. I didn't want to discuss, and she's very good at marketing. So I said, okay, I'll take 13. But I secretly snuck back to my workplace, fired up my AI, and asked, well, I'm going to have this talk. And I have 16 kind of things I want to talk about. And how about me picking 16? I almost cheated there. And it came back, and it said, no, pick 13 or 17. And I was like in shock. I was thinking that, well, not only AI is hallucinating, but also my wife. But anyway, 13 it was, and my speak was accepted, so I guess that's good. But this is just a marketing figure. It's not 13 in the real case. Okay, and then it's a summary. And before the summary, there is a secret kind of item, agenda item that I'm going to surprise you with in the end. So stay awake. Okay, here are some metrics in the temporal domain. That is something that has to do with time. We often talk about average throughput, which is the number of operations we can do per second, or perhaps it's the number of megabytes that we can, drive through some kind of communication protocol or something like that. Another thing is latency. Remember the bars we spoke about in the beginning. Latency is often reasoned about as the typical latency. So if you have 1 million measurements of delay, you order them in the size, and then you pick the middle one. That's the typical one. But sometimes you are more interested in the worst case. What if you have customers? They don't want to experience the long waiting times. So usually you can use something called like 4 nines. So then you can do, again, 1 million samples, and then you take away 100 of them, and the highest that is left, that's called the worst case. And that might be measured in, milliseconds or something like that. And usually, if you want to optimize for latency, you do different things than if you want to optimize performance. Sometimes you do something contra-intuitive that can give you better latency, more predictable latency, but will give you less throughput. So they are different optimization criterions. Okay, startup time is another thing. Startup time is defined as the time it takes from where you launch your application until it produces its first result. In a more realistic case, it's like you deploy a web application, and that's the time it takes before it can serve incoming requests. So that's the startup time. The warm-up time, however, is something different. That is the time it takes from when you deploy your application until it provides peak performance or almost peak performance. And as you know, and I think you know, the Java application is a bit slow in the beginning, and then it picks up and gets faster and faster. Okay, there are other resource metrics, of course. How much memory is my application using? If you have a sorting algorithm, it might be use more memory, but trade that against speed. The memory access pattern is another thing. If you have two matrices, big, it's a very big difference on how you arrange your operations. It will produce the same result, but maybe it will double the speed if you do it in a clever way. Memory pressure is another thing. If you allocate a lot of objects, they need to be collected and created on the heap. That's usually bad. Thread usages, okay, if you can do something with 2 threads, that is better than 4 threads. That's a win, of course. That's a resource. Contention is another one. Maybe you have some centralized resource and you need to serialize access to that resource. Then that can create contention. Code size is another trade-off. If you have a small loop, you might do stuff that you unroll it, for example. It might be the case that your code runs faster, but you allocate code space, which is not always good. It's a trade-off. Another more recent thing is SIMD operations. Now, SIMD stands for single instruction, multiple data. And that is what you usually call vector operations. That I think every modern CPU has these of various sizes. But that's also scary resources. Some CPUs share SIMD registers. Some CPUs will clock down when you use them, so that will impact other areas of your code. So there are some things to think about that. And I think it all boils down to the efficiency, the energy efficiency of what you are doing. The amount of energy it takes to create each amount of useful work. And in the world we're living in with scarce resources, this is important. Okay, platform is another one. We have different CPU types. They have different steppings. And the CPUs have different compute retrieve ratio. When I started to code in Java back in 1.0, the ratio was about 1. So if I would add 2 ints, for example, it took 1 clock cycle to load A, 1 clock cycle to load B, and then 1 clock cycle to add them together. But that's not the case on the modern hardware. Of course, the clock cycle now is much faster, but just retrieving from 64-bit from main memory will set you back about 100 cycles. And maybe adding them together is just 2 cycles. So it's relatively speaking much more expensive to get things from main memory, and you should try to optimize your algorithms so they can keep data local. Number of cores, of course, is an important thing. The cores are interconnected. That's sometimes good, sometimes bad. If you have several chips or dies on your server, they are living in basically different spaces and they need to communicate via high-speed bus. So that's another concern when you deploy your application. OS type, of course, will affect and which kind of garbage collector you selected. Okay, and of course, the application you're running is very important for your performance. Workload, data shape, and that can lead to something called pollution because Java kind of records profiling data, and if you suddenly change how the data is shaped, your program will run slower again. We will talk more about that later on. Okay, so let's sum up the metrics. Usually we optimize average throughput in steady state, that is after warm-up. If it ain't compiled, it's hardly used anyway, so it doesn't matter if it's slow if you only call it once or twice. For example, class initialization is by definition only executed once, so it might not be that super critical. Whereas in other cases, if you are calling loading stuff from disk or from memory, it's very important that they get compiled in an optimal way. We have these supported platforms. We have Linux, A and X, Max, A and X is kind of sunsetting. Windows X, of course. Everything is 64-bit these days. And of course, we shouldn't forget our porting friends that is struggling all the time with keeping up with the performance improvements with RISC-V, PowerPC, S390, and so on. They are doing a great job for the community. Okay, so there are some challenges when you are measuring performance. Don't use a laptop, for example. It's likely not a representative target of when you deploy your application on a server. It has power management. It depends whether or not you put in the charger. And I can tell you a thing that happened to me a long time ago. I was having a kind of a baseline, and then I thought that, I want to make this clever optimization. So I first ran the baseline, and then I applied my changes, and then I ran my new benchmark expecting a much better result. But I was very disappointed when I came back. It was worse, despite all my efforts. And I got frustrated, scratched my hair, went to get a cup of tea, got back, and in denial, almost, I ran the test again. And now it came out much faster. And of course, the reason for that was that my first run heated up the computer and the CPUs were throttling down. So that's a lesson you can learn. Run the method 30,000 times before you're measuring, because otherwise it doesn't get compiled, and then you don't have a representative figure for your code. And don't use system current milliseconds, because that can actually go backwards. It's not a monotonic timer. It gets adjusted when the network time protocol, for example, kicks in. So it's better to use nanotime. Not only that, but it performs better resolution. And it's actually the case that several times a year we got mail that some guy writes that, and it's usually a guy, writes that this method A is slow. Look here, I invoke current milliseconds, I invoke A once, and then it's slow. Yeah, of course it's slow because it's not compiled and it's not designed to work that way. So don't do that. The JVM can also infer constant, folding, and speculate. Speculate is something we should discuss a little bit. It is the case that the JVM can bet on a certain kind of input. It learns statistics and then it can bet on the input and do some optimization. That's called speculating. And yeah, don't write your own test framework. There is one out there called JMH, which will fix everything of these bullets for you, except, of course, then for the laptop part, because that's up to you. Okay. Okay, so let's look at some compiler tricks that the VM can do for us. And I think this section is kind of what I call thrill or chill. So it's a bit advanced. So if you think this is kind of a bit over the top, you can just chill, and then you can come back in the next section. So this is the circle of life for Java code. So when you start your code, it starts with interpreted bytecode. It reads every bytecode and checks, and it decodes it, and then it mutates the state of the VM. And it comes back, reads the next byte, and needless to say, this is very slow. So the VM will discover that my method is being called a lot of times, so maybe I should compile it. And then it's using, I wouldn't say a simple compiler, but it's using a compiler that is not producing optimal code. Instead, it's producing code that allows us to run faster, but also collect statistics on how our program runs. For example, if something is null in a reference parameter we have to a method, and it might be the case that it's never null. So then we advance to the next step. After like 30,000 invocations, we know that this parameter is likely never null. So then the C2 can speculate and say that, well, this is probably not null, so I will install something called an uncommon trap. So if it's actually null, it will kind of explode. But if it's not null, it will just run this optimized code. And if this triggers this uncommon trap, we will just optimize, evict the code cache, and go back to interpreter mode and try again. So that means that if our speculation pays off, well, that's great, we get better performance. But if it doesn't pay off, well, then we're back to where we started at least. Okay, so this is kind of a Rosetta Stone for compiler nerd wannabes. Tricks that we can do to get your application running much faster. We have inlining, loop unrolling, hoisting, dead code elimination, auto-vectorization, superword. And I will do some examples here to tell you a little bit more about that. So let's take a look at the method at the top. This method is called copy, takes a byte array source and a byte array destination. And it iterates over the source and just copy byte by byte from the source to the destination. It's a very simple method. And then after that, I go about and create a source array. And then I create a destination array, which is empty, but has the same length as the source array there. And I will copy. Okay, so when the VM has seen this and determined that this is happening a lot of times, it can do something called inlining. It can remove the invocation of the method, so I don't have to put those arrays on the stack. And then it can do like this. This is equivalent in terms of operating in terms of my algorithm, but it's not equivalent if something happens, if an exception is thrown, for example. So the VM needs to keep bookkeeping of this, that if an exception is thrown, it needs to unroll all these changes so it can produce a stack trace that is correct. Then I can do something called loop unrolling, and that will kind of amortize the cost of going back and forth in this loop. So instead of doing one operation, I can do, for example, 4 operations. And that means that I only have to do this check if I'm is less than source length 25% of the cases. And you might think that, well, instead I have to do this adding. Isn't that slower? And the answer is no, because this I less than source length is a branch operation, which can be very expensive for a CPU, because if the speculation on the branch fail, then it will be very, very costly. And the ... at the end means that we have to have a cleanup operation. Maybe my source array wasn't equally divisible by 4 in length, so then you have to do some cleanup. I didn't show it here. But we can do better than that. If you remember in the last slide, for every access we do on the array, we need to check the bounds. So we need to check the destination bounds +0, the destination bounds +1, destination bounds +2, and so on. But we can hoist that check. And we can check from the beginning that is length greater than destination length? No, and then I can throw an exception. And again, this is not really the same as before, because if something happens down the line, we will not see the exact line number, but this is just to illustrate the principle. And instead of brackets there, I've used parentheses to symbolize an unchecked array access. This, of course, doesn't exist in Java. This is just my way of showing that now we don't have to check the bounds. So there's one check at the beginning, and then everything is unchecked. And as before, we need to do a cleanup operation. But we can do better, even better than that. We can see that the destination length is always equal to the source length. So we can just eliminate this check. It's redundant. So that makes our program even faster. And then instead of doing copying in units of bytes, we can do copying in units of longs instead, which is 8 bytes. So maybe there is kind of an internal method that allows us to view this array as a long array instead. And then we can step 8 bytes per operation. And of course, this is much faster than just doing one at a time. So now we're starting to getting somewhere. And of course, long isn't the biggest one. If you have one of those more modern CPUs, we can have up to 512 bits operators. So we can say that I want to load 512 bits of data from the address of source, and then I want to store 512 bits at the address of destination plus I, and then I can step up 64 bytes for every time. That means that we have much, much less checks in the loop. But that's not the end, because we can now apply hoist and unrolling again. So we can say that, yeah, I want to pin my source and destination. That means that the GC cannot move it. And then I can get the address and for the source and destination outside the loop once and for all. And then I can unroll these operations here. And I think these operations can translate to just 1 or 2 machine code operations. And then they just roll out this, and then we can go back to the loop. And now it's 1 check per 256 bytes, which is 0.5, around less than 0.5% of what we had in the beginning. So of course, this will be much faster. Okay, back to the 13 performance improvements. I think that's why you're here to hear about. So starting off, we take a look at those JEPs that's been integrated from 21 to 25, and that's a lot of them. We have hotspot changes, flight recorder, garbage collectors, JIT compilers, runtime system. We have language changes, changes in the library, security updates, some tools. We have preview functions, like in languages and libraries, and then we have deprecations and removals. And I will start backwards, and here you have a QR code for if you want to check this kind of list with all the JEPs. Deprecation and removals is important, but because if we didn't have that, the JDK would grow and grow and grow and become eventually unmanageable. So we we deprecated the sunMISC unsafe and saying that eventually we will remove this, but we won't do it now. We will only do it when we have something that is equivalent for this, and we are working on that. We deprecated all the 32-bit stuff, and we also removed that from the JDK, which means we save space and maintenance. And there is one, I would say, big change in terms of deprecation, and that is the security manager. The security manager was, I think, not that much used, especially when we don't run Java in browsers anymore. But it was kind of having its tentacles all the way in the JDK code. For example, if you want to check a parameter, you have to do it in a kind of a privilege mode. So therefore, you had to create some kind of lambda or a kind of a function that returns something and run that. So when you start Java, all these kind of anonymous classes were created, slowing down the startup. And it also, when we removed it, everything looked much more simple and manageable. So that's great. And there was a separate story about Inside Java podcast on deprecation and removals. And here you see a Dr. Deprecator talking about this. So you can go there and check it out if you're interested in that. Okay, JFR method and tracing. This doesn't improve performance at all, but it gives you a microscope into your application when running live code on your target hardware. So I spoke about benchmarks before, and you run them kind of artificially on the side, But with JFR method and timing, you can actually run your code and gather statistics on live data on your deployment platform. And here is an example of how you can do that. You can say that I want to know, when my resize is being called. And then every time that is being called, you get a thread dump. And that can give you an idea why is that being called. Excuse me for a second. Okay, and then maybe somewhere in the J2 demo, you can create a hash map with a bigger size, so you don't have to invoke this resize anymore. You can say that I'm interested in the class loading statistics, and here you see that all my classes are loaded like this, and then you can target, and maybe you can initialize them in different threads or whatever you're doing there. I see actually that there's a security manager stuff snuck in there, but maybe that will be removed eventually. Okay, late barrier expansion for G1. This is kind of a low-level thing. I won't go into the details here, but you might know that your application are running in threads, and the GC is running in other threads. And because they need to have a consistent view, there need to be some kind of barriers between memory that's being mutated. Otherwise, they wouldn't see a consistent view. And this is related to how those barriers are generated. Previously, they were generated early in the compiler process. Now they are generated late. And this is something that was influenced by the ZGC garbage collector. So this not only makes the compiler more efficient, but it's also easier to maintain because now it's more like how the ZGC, which is a more modern garbage collector, works. And this is important in cloud applications because now compilation will be less expensive. Region pinning for G1. I don't know if you are running a lot of code that is using JNI critical regions, like you are calling native methods very extensively. Maybe you have 100 threads that's doing this. And if there is just one thread previously that were in this critical region, the GC couldn't run. So eventually, if you had many threads, you could end up in a situation when the GC got starved and couldn't run or got delayed for a very long time. This was fixed with this one, so that means that the GC will run much more smoothly and will keep your heap much more tidy. ZGC, generational mode by default. Well, I'm going to talk about first what is ZGC and also removing non-generational mode. So now you can only have generational mode, not non-generational mode, and that's good because now the guys and girls can focus on that. So the ZGC is used if you have larger heaps, if you have heaps in the terabytes. That's not possible to have with the other GC, the C1. And it has short to stop the world events. And it was introduced in JDK 15. And the generational variant was introduced in 21. And now in 23, it was on by default. And we removed the non-generational in 24. So let's look at how a generational GC works. So let the big ring here represent the heap. And the objects you are seeing here, the square and triangle and so on, are old objects. And now we create a new object, the star here. And, well, every time you create a new object, the GC has to inspect all the objects in order to see if one object is not referenced anymore. So that is quite expensive. And if you are considering that you have, caches in the CPU and stuff like that, it's kind of a disaster. It will create a storm in your computer or server when the GC does a full scan of all the objects. It will ruin your caches. So new objects and old objects, they live together. And if you look at the objects, they usually are distributed like this. It's sad to say that new objects die young as opposed to humans. But that's the fact. It's the fact that it might even be the case that objects are not even created on the heap because they are a representation of them and created on the stack instead. But so therefore, it's better to have two kind of regions. One when we have new objects and one we have older. So now our new object is created in this new space and the old objects remain in the old space. And if you look at the probability now, because when a new object has resided in the new part for a certain amount, it gets moved to the old part. So now we know that every object sitting there is new and more likely to die. So it's better that we spend the resources there. And not only that, because they are new, they are likely in the CPU cache. So we don't have to touch what's outside the CPU cache. So that's a much more efficient operation than scanning all the old ones. Now for the old ones, it's the same, but on the other way around. So I was born in Sweden in like 60 years ago. And at that time, the expected mean average time to live was 73 years old. That was pretty good at that time. But now it's 10 years more. It's 83 years old. But as I'm standing here in front of you, I didn't die. So that means that all that probability up until now goes out of the window, luckily for me. And now I'm expected to live like 85 years instead of 83 years because I didn't die. And it's the same with objects. Because they didn't die, they are likely to live longer. And so we can spend more time here and we can spend less time there and still be more efficient. So that is great. And that's the theory behind generational GCs. Okay, here is an interesting one, compact object headers. So what is an object header to begin with? Well, the GC needs to store some information about each and every object when it's tracking objects, for example. We have the type system. How could you do instance of if you couldn't associate it with a class? Reflection, all that stuff predicates on the fact that we can determine what kind of class is this object of. We have locking, so you can synchronize on any object. We know that. And because of that, we need to manage that kind of information necessary for invoking such monitors. We have hash code. I mean, you know that if you can't afford to write the hash code, one will be provided for you. And that kind of hash code needs to be stored somewhere. And many people think that the hash code that is created by the system is the address, but that's not the case because the GC can move around the object all the time, but the hash code stays the same. So it needs to be stored somewhere, and it's stored in the object headers. And it used to look like this. So you have something called a mark word, where you have some unused space, and then you have this hash code, if it's used. And then you had some ages, and then a tag. The tag is used for, like, if you want to have some more, like a contended monitor, for example, you need to have more information that can actually fit in the mark word. So then you inflate this one and create something, a data structure on the side, to which you copy the hash code and all the old stuff, plus a lot of additional information. And once you exit the monitor, you can restore that back again. So we come back to the original layout. We also need a class word, which almost always is compressed, because I haven't seen one single application that doesn't fit in this kind of compressed world. So that means we have 96 bits. Now, the compact object header looked a bit different. It squeezes everything into 64 bits. And if you look very carefully, you can see that we have slightly less class pointers here. So that means we can have a little bit less classes, but I don't think that will be a practical problem anyhow. We have the hash code, and we have some other bits that is used slightly different, but that's outside the scope of this presentation. But the conclusion is that we can go down from a size of 96 bits to 64 bits. And that means we can have a 33% reduction of the header size. Not bad. And if we look at the realistic pace, maybe a small object like record index int y, that's 64-bit, and together with the object, now less object headers, we can go from 160 bits to 128 bits, which means there's a 20% object reduction, which is not bad. And this, of course, can translate to money, because now I can run virtual machines or Docker instances with less memory. But that's not the big kicker. So let's look at how a modern CPU looks like. Maybe we have like 4 cores, or we have a lot more than 4 cores, but I'm illustrating 4 cores here. And every core has an L1 cache, which is typically very fast. You can access it in maybe 2 or 4 clock cycles or something like that, but it's very small. Every core has its own L1 cache. Then there is an L2 cache, which is bigger, but unfortunately a bit slower. It might be like 10 cycles to access this one, and sometimes this is shared across several cores. That is good in one way, because if you want to communicate between core 1 and core 2, that's faster, because now we can do it via L2, but it's also bad because if they're doing different things, they compete for the same resource. Then there is an L3 cache, which is significantly bigger than the L2 cache, but it's even slower. It's like 20 cycles to access thing here. This is just exemplary figures. And then, of course, we have main memory, which is like 6 orders of magnitude bigger. But here we might be hit by 100 cycles to read 64 bits or even more. And we also have something called TLB, which is a translation look-aside buffer, which allows the cores to translate virtual addresses to physical addresses. I mean, imagine if you had to do 2 memory access for one, that would be a disaster in terms of performance. But that was taken care of by the TLB. Okay, what happens now if we have smaller objects? So the L1 cache will now be freed a bit. So we have, if the objects are 20% smaller, we have 20% more space there from which we can move things from the L2 cache into. And now that the objects are smaller, we can move more objects into that 20% than we could before. So that means that we will free up more space in the L2 cache and so on. And the L3 is the same there, and we can move memory into the L3 cache, which makes the CPU much more effective. And because our total memory size will be about 20% lower, the TLB will also be more efficient. Maybe we can now fit the entire working set into the TLB and never get hit with the cache misses there. So we have some experiments and anecdotes. In one setting, the spec job used 22% less heat space. That's similar to the 20% I was talking about, and 8% less CPU time. Great. In another setting, the number of garbage collection was reduced by 15%. Of course, now we have less garbage to collect, so that is good news. A highly parallel JSON parser runs in 10% less time. Wow, great news. But I'm always a little bit suspicious when I see, in one settings. Well, maybe there were other settings when it wasn't that great. So I encourage you to take it for a spin. With your application, you can just provide this use complex object headers, and off you go and see what happens. Okay, Product Laden is an effort to reduce startup time, reduce warm-up time, and reduce footprint. And there we have 3 delivered JEPs: ahead of time class loading and linking, ahead of time command line ergonomics, and ahead of time method profiling. Class loading and linking is saved. So you do a test run of your code. That is saved into the AOT cache. And when the program starts up the next time, it can just memory map those kind of the pieces of information, and you can start off much quicker. The middle one isn't a performance improvement. It just makes this process of running the test run and creating this AOT cache file easier. And the last one, ahead of time method profiling, is important because, well, if you didn't chill, you remember how this looks like, the interpreter C1 and C2. And now that we can get this kind of profiling data from this auxiliary cache file, we can much faster move from the interpreted and C1 phase onto the more optimal C2, and thereby reducing warm-up time. Okay. So in one case study, I was here last year and talked about Laden. And in that case, we had a 2x startup improvement for just compiling Java files. Don Hedigan spoke about this at Java 1, where he observed 4 to 2 times improvement in startup time for some of the most common microservice frameworks. And you can go there and watch his talk if you want. And this is kind of a tire just waiting there to be kicked. Try it out if you are concerned about startup and warm-up time. The foreign function memory API is something I've been working with a lot personally. It allows you to call methods directly from Java, which is called down calls, or vice versa, up calls. And you don't need any JNI, you can just call. For example, if you have a system method like fread, you can call it directly from Java. And up calls can now be more than 2x faster, and down calls can be at least as fast as they used to be, and you can do some tricks if you allocate memory, for example, and improve performance even more. Foreign function memory gives you additional guarantees. It gives you temporal, spatial, and optional confinement guarantees. What does that mean? Well, a temporal guarantee says that if I allocate a slab of memory, I can use it, but then when it's closed, I can't use it anymore. If I try to do that, an exception will be thrown. And that kind of eliminates the risk of use after free. Spatial is another one. It's now not possible to address outside this memory slab. And if you try to do that, you will get an exception. And the confinement guarantees are that you can say that, oh, I only want to use this memory segment for this thread. Because if you read it from another thread and you don't have this kind of memory barriers, you can get false share the wrong information. And this is much faster given the guarantees. But is it faster than unsafe? And the answer is no. It's like if you have a Formula 1 car and someone come up with a bright idea that, well, we can remove the roll cage and the safety belt. Wouldn't that make the car faster? Yes, it would, but no one would probably do it. And I think it's the same here. Use the foreign function memory API, and then you have the safety belt and the roll cage. There's another tool called JExtract that can generate bindings automatically to C libraries. For example, if you're an AI library, you can just kick off JExtract and it will generate all the bindings, and then you can just go about in code and invoke those methods directly. So that's a cool thing. And it's production ready now. A lot of prominent third parties are already using this. So Netty, Lucene, Tomcat, Rust, and a lot of others are doing this, Scala. So try it out. Stable values is another thing I've been working with. So stable values is a safe wrapper around a stable annotated field. And that leads to the next question, what is a stable annotated field? And this is something we used heavily in the internals of the JDK. It says that when the VM comes to a field that is stable and it's not a default value, the VM is free to inline that value because it's guaranteed then that it will never change anything in the future. And that unlocks a lot of performance potential. But you can't use this in your own code because it's inherently unsafe. And this is what stable value does. It allows you to use the same speed up things that we have internally in the JDK in your own code. It's API based, similar to thread local, scope value, and class value. And it guarantees atomic at most once mutation. So a stable value can be created using a computing function. And on the first access, the value becomes computed and initialized. It's only when it's used when it's initialized, so it's lazy. And an initialized stable value supports the same optimization as a final field. That is, it can be constant folded, for example. So before this, we have this tension between laziness and immutability. And it's like you have to choose one, lose one. But now you can pick them both. So this is a very interesting concept that we are working with. It's still preview. And you can have a stable value like this, which is a single value. You have stable value of type logger. And there on the right-hand side, you have the recipe for creating that logger. But it's only when you invoke get that logger is actually being created. And you can have a lazy list. You can have a list of size. And then you can create a bunch of loggers. And then maybe you can, depending on the thread ID, and you can do modulo size, you can get different loggers if they have like a scarce resource, for example, that cannot be shared so easily across threads. Or there is even a lazy map. So you say you have test integration, internal and production, and you can then use a lazy map saying that I have all these, the set of strings there, and then I create a separate logger for those. And then I can invoke get with my thread name. So if I have, for example, integration, all the integration will have a separate logger, the production will have another separate logger. And all this can be inlined. So my logger.get will be constant folded and just point to the original, actual logger. Okay, we are approaching the end. This is synchronized virtual threads without pinning. Before this, when a virtual thread hit a synchronization, it needs to be pinned to its carrier thread. And that impacted or severely impacted the scalability of virtual threads. So the recommendation was to not use synchronize, but instead use a lock. But this has been fixed in 24. So now we can lift that recommendation, and virtual thread will work just as a normal thread in terms of doing this synchronize stuff. So that is great. And there is a bunch of other non-JEP performance improvements. There are literally hundreds of them coming in all over the place. So I won't have time to go through each of every one of them. And of course, if I would have done that, it will be considerably more than 13 items, which I promised. So that's another reason. But Claes and I have the ambition to every Java release to write a performance paper on what are the actual things that's included here in terms of performance. So if you're interested in performance, and I guess you are, otherwise you wouldn't be here, maybe you can go to Inside Java. We expect to release the article on JDK 25 in a few weeks. Okay, so now we come to the secret kind of point. Sneak peek in JDK 26 and beyond. So what might emerge in JDK 26 and above? So Leiden will continue to work. Leiden is not finished yet. We will, maybe have the opportunity to cache objects. We will have opportunity to actually store machine code, compile code from the C2 directly into the AOT cache and start off with compile code directly, which will even further reduce the startup and warm-up time. We have Valhalla. Remy had a presentation just today about Valhalla and value classes, and they will kind of allow flattening data structure and in arrays, and you can create objects that are not actually existing, but it's just a semantic notation around primitive values. We have C2 auto-vectorization improvements. You remember if you didn't chill, you remember all the optimization C2 can do for you, and we have improved them. There, Emmanuel Peter has done a great job doing that for us. So that is likely to come in 26. It's integrated already, and unless we back it out, it will be there. And for the Panama foreign function and memory API, we're going to see continuous improvements over the time, so we can narrow the gap to unsafe. Okay, so I encourage you to go to Oracle or your favorite provider of the JDK and download 25 and try it out. And if you're interested in what's happening with the JDK, you can go to Java 1 and register for notifications there. And with that, I would like to thank you for your interest and open up for any questions, if there are any. Thank you. Okay. Okay, yes? Yeah. So the question is, what is actually if I interpret you correct, what is the impact of compact object headers? And I think the answer is it depends. It's very, dependent on how your application look. Are you working with huge objects? Then it probably doesn't matter so much because the header is just a small fraction. If you are working with small objects and you have a certain workload, it might be a rather big difference. The standard benchmark. Yeah, okay, so your question is more like how much of those 5% are attributed to compact headers? Could be a product better. Okay, that's a good question. I don't know the answer. Okay, yes? Yes? That's a very good question, actually. The question is record components stable? Are they trusted? And the answer is yes, they are. Because they enjoy special protection by the VM. You can't, for example, use reflection to change them. If you use the set accessible true and you try to change them, it will blow up. So they have a certain privilege operation. They, records together with anonymous classes, have this feature that you're talking about. So yes, they are trusted. And they are immutable, so they are not really comparable to stable, because stable allows you to have a mutable field, which is trusted. But the record is, of course, immutable from the beginning, so therefore it's not really stable, but it shares the principle of trustness, like you rightfully say. So that's a good question. Okay? Okay, thank you very much, and if you want to talk with me more, I'm here. Okay, thank you.